Hello everyone, part 4 of Carbanion chemistry, that is basically continuation of part 3 where I have started stability of Carbanion. Now some more information related to stability of Carbanion we will see in this video. So these factors I have already covered, that is the factors responsible for stability of Carbanions. So these are covered in the previous video, which is basically part 3. Now one question we have after all this discussion related to stability factors, that how do we know which factor is more important when we will actually decide order of stability of Carbanion. Suppose 3 to 4 Carbanions are given and it is asked that find the stability order, then how these factors will actually play their role, because some factors, that is which factor we should give more importance, that is the question. So what happens sometimes that they can interact with each other in unpredictable ways. So it is not very easy to conclude which factors we should give more importance. It is normally that aromaticity we give more importance, but not if some other factors may sometimes it can overcome also. Though that is rare, but still they can interact with each other in unpredictable ways. So that is the reason it is difficult to conclude which is most important. Thankfully, we can use the concept of basicity, because Carbanion you can consider as if it is base, and if we know its basicity, that is whether it is strong base or weak base, then we can figure out the stability of these Carbanions. Higher is the basicity, that means when it is very strong base. So strong base means it is very reactive, that means higher is the basicity. So when basicity of this Carbanion is high, and these bases are basically generated from carbon acid. So in general, if you write the structure of Carbanion R3C minus, where R may be any substituents, and this is basically generated from R3CH. So this R3CH is basically the carbon acid from which the Carbanion is generated. So higher is the basicity of Carbanion, lower will be its stability. Okay. But the question is, how do we find a good measure of basicity? So for good measure of basicity for this species R3C minus, basically we have to focus on the acid, corresponding acid, which is R3CH. We can also write it for simplicity as if it is RH. So here we have this carbon acid from which after removal of this H, this Carbanion is generated. So it is basically the conjugate base of the acid RH, of the carbon acid RH, or you can write it as if it is the carbanion. So whenever you are getting any Carbanion, just think about, just attach one H, then you will get the corresponding carbon acid. So higher is the stability of this Carbanion, that means higher stability of this Carbanion means what? It is very reactive. Now it is very reactive means what? That the equilibrium, it will always try to remain on this side, that is RH. Now if R minus is very reactive, then equilibrium will be in the left hand side, that means RH is not very acidic, so it will not remain in the dissociated form like R minus and H plus. But if the Carbanion is very stable, that means if the conjugate base of this RH is very stable, that means the equilibrium will be mostly towards right hand side. So RH, it will be remaining in the dissociated form, R minus H plus. So that is why it is written here that higher is the stability of the Carbanion, higher is the acidity of the acid, it will remain in dissociated form mostly, and lower will be pKa, because acidity and pKa, these two are inversely related. Fine. So stability of Carbanion, it has some relationship with pKa, right? So the factors that determine the stability of Carbanion, you can also say that it can also determine the order in pKa of the carbon acid. Now if we say in reverse order, if we make the statement that pKa of carbon acids, suppose we know the values, so from pKa also we can predict what will be the stability of Carbanions, because pKa mostly if we find it from data, then we can understand what will be the stability of the Carbanions. Fine. So here we have these three species, as if all these are basically, try to think in the format of RH. So if all these are RH, what I will do, I will just remove this H. So suppose this, the corresponding R minus. So I am basically writing all the R minus that will be generated from these three species. So here we have negative charge, then I am breaking this CH bond. So this is the corresponding R minus, and here we are breaking this CH bond. So the R minus will be PH3C minus. So these are the corresponding R minus if you are considering all these three species as if it is RH. Now pKa values are given. So lower pKa means what? This RH, that is, this is very good acid, so it will mostly remain in this form. So it is very stable. Now the next pKa 25, that means it is in intermediate value, having intermediate value. Now compared to the first one, it is the corresponding carbonate is less stable, but compared to PH3C minus, it is more stable. So R minus stability for these three species, it will be like this. The first one maximum, the second one it is intermediate, and finally the lowest stability, that will be for PH3C minus. So if we know the pKa values, we can directly find the order of stability of the carbanions. Now individually I will consider some effect, that is, suppose I am first considering inductive effect, as you can see it is written here, then suppose another effect, conjugation effect, and the third effect, aromatic city effect, that is whether this carbanion is aromatic or not. So these three are the main important points. So in this examples, total 5 species given and the corresponding pKa values in DMSO solvents, that values are given. So inductive effect if we consider, then we will have some, that is stability order, but we will try to see whether it is matching with the information that we are getting based on pKa only. So if you consider pKa, here lowest pKa we are getting, suppose I am giving the number, it is 1, 2, 3, 4, 5. So as it is having lowest pKa, that means when you are breaking this bond, which hydrogen we will remove, that is already it is drawn separately. So this hydrogen that I have just marked, you have to remove those hydrogen. So think about the corresponding carbanion. So that carbanion which is generated from 5, that will be having maximum stability. After 19.4, the next value, it is for 28. So species number 4, that is a carbanion that will be generated from 4, that will come next. So 5, 4, after that there is 29.0, that is the first, and then we have 30.7, which is species number 3, and then we have 2. And if you think about from the inductive effect, here this PHSO2 group, let me change the color. Here this PHSO2 group, that is basically common for all, right? So what about the other group? Here we have N plus Me3, which is highly electron withdrawing. Then for the species 4, we have F. Here it is N Me3 with positive charge. These are the substituents that is basically different in this all these 3 species. Then in case of 1, we have H. For 3, we have OMe. Now OMe basically because of the presence of lone pair over oxygen, it will show Plasser effect. So that is why compared to H substituent, 3 is coming next after 1. And then for 2, we have this inductive effect, that is plus I effect. So electron withdrawing effect is maximum for NMe3, then F, then H, then OMe, and then Me. So this prediction you can also do from inductive effect consideration, that is plus I effect present or minus I. But if you see from pKa value also, we are reaching the same conclusion. Okay. Then conjugation or pi delocalization. pKa values are mentioned in DMSO solvent. Now the lowest pKa that we have in case of this one, that is number 3 species, that will be maximum stable, that is a corresponding carbanion if you remove this hydrogen. Then after 26.5, next value it is for this one, this hydrogen it is mentioned. So it is 3, then we have 4. After 4 it is 31.3, that means species number 5. Then species number 2, 43, which is basically toluene. And at last methane. So this is the lowest, the corresponding carbanion, which is basically CH3 minus, that will be having lowest stability. So from pKa you can do this type of prediction. But what about conjugation? So see here, if negative charge is generated, conjugation is possible. Here also it is possible, but because of this donating group, it will be lesser compared to the previous species. Then we have, after 3, 4, we have 5. Here also conjugation possible. Then in case of CH toluene, here after removal of one hydrogen, there will be negative charge. Conjugation with the double bonds of benzene ring possible. And then in CH4, there is basically no conjugation. So from this effect, that is conjugation effect also, we are reaching the same conclusion. Just like from pKa also, you can reach the same conclusion. And the last one, it is basically based on aromaticity. The aromatic ions show a level of stabilization far above that of normal conjugated system. So this information, if you look at the pKa values and the pKa values that you are getting here, 18, 20, 22, 30. So it is in between 15 to 30. But if you look at these values, they are basically also the first example. They are compared to the last one, their pKa values are high. So this statement, it is basically trying to say that previous all the carbanions that you are seeing, compared to them, when it is gaining some aromaticity after deprotonation, so obviously it will be showing more stability, more stabilization. So that is why we give more significance to the factor whether it is carbon, that is carbanion is aromatic or not. So here we are having aromaticity, so that is why pKa values are so low. But now we will try to find from pKa which will be the having the lowest stability and high stability. So this is minimum. Here actually the sequence is maintained 18, then 20, 22.6 and 30. So this is the basically from all are, there is aromaticity factor, but still there is some difference. So based on that we are having this stability order. The values are not drastically different from each other, only this one is different because here the carbanion that will be generated, it can undergo that is conjugation is possible in both three. But here if you are having this, we have some one sp3 carbon still, but here all of them will be sp2. So that is why though individually aromaticity is possible, that is these two rings are aromatic, and then this negative charge can also undergo delocalization individually with this ring, but compared to the first one it is having lesser pKa, sorry, higher pKa. That means the corresponding carbanion will be not so stable like the third one. Fine. So these are the three individual effects we are considering, and we are trying to see that the result that we are getting from pKa, whether it is matching or not, and it is matching. Fine. Here this is the last slide, and here you can see some examples of carbanions along with their orders that are mentioned. So first one obviously aromatic, then here we have this S character, here we will have conjugation present. So these are the different factors you can see in all these examples, and this is the last one because all these three groups are having plus I effect. Okay, so that's all in this video. Part 3 we have started the stability of carbanion, and in this video we have some more information. Okay, so if you find it helpful, please like, share and subscribe. Thank you for your time.